Hello and welcome everyone. We are excited to have you join us today for an insightful session. It's a pleasure to bring you this webinar and we are glad to feature Urmi, one of our finest engineers. She has been on the team for an extended period of time. Also, we encourage your interaction. So if you have any questions, don't hold them back. Drop them in the Zoom chat anytime and we will address them during the QA segment. Let's jump right in. I'm now passing it over to Urmi who will get us started. Hi Urmi.
Mm. Hi. Hello everyone. I am Urmi Biswas, a software engineer at AppsCode and I work on the KubeDB team. Today I will be talking about Milvus, which is a vector database, and how KubeDB makes deploying and managing Milvus on Kubernetes. Here is a quick overview what I am going to cover today. Firstly, I will briefly introduce what Milvus is and its usefulness, and then we will look at some of its key features. After that, I will show how we can provision Milvus easily using KubeDB on Kubernetes. Following that, I will show a short live demo, and finally, I will wrap up with a QA session. Now, Milvus key features. Milvus is mainly designed for efficient similarity search over billions of vectors. It supports ANN hybrid range filtering search. It is built with a cloud native horizontally scalable architecture. It offers both standalone and distributed deployment modes. It integrates multiple high performance vector indexing algorithm along with enables cost effective storage with hot cold tiering and multi tenancy. Now, Milvus use cases. It mainly empowers semantic search and RAG based AI applications. Also helps with building real time recommendation systems and detecting anomalies and fraud using vector similarity. It also enables image, video, and multimedia similarity search with accelerating document, patent, and knowledge base search. Now we will see what KubeDB is going to offer for Milvus. With KubeDB, provisioning Milvus becomes very simple. Instead of manually managing manifests, we can deploy a production-ready Milvus standalone and distributed mode using a custom resource. KubeDB continuously monitors the health of Milvus. The health checks are customizable, which helps detect failures easily and maintain stability. And KubeDB allows user to apply custom Milvus configurations easily, so we can adjust database behavior as per our needs. Authentication credentials are managed securely using Kubernetes secrets, keeping sensitive data out of configuration files. We also have support for production ready versions such as 2.6.7, 9, and 11. KubeDB offers flexible deletion policies, so we can control whether data is retained or removed when a Milvus resource is deleted. Finally, KubeDB integrates with Kubernetes persistent volumes, ensuring that our Milvus data remains safe even if pods restart or remove. This diagram mainly shows Milvus operator on Kubernetes. Starting from the user applied Milvus custom resource at the top, KubeDB watches this resource and takes responsibility for everything else. Based on the Milvus CR, KubeDB automatically provisions all the required Kubernetes components, including pet sets, services, secrets, PVCs, PDB, and app binding. Together, these components run a fully functional and production-ready Milvus cluster. At the bottom, you can see deletion policy. This control what happens when the Milvus resource is deleted. If we choose wipe out, it deletes everything including secrets and PVCs for ensuring complete cleanup. And if it is hold, then it retains secrets and PVCs, and for delete, it only retains secrets. And if we choose do not terminate as deletion policy, it rejects the whole deletion process. Okay, here is our live demo section. In this, I will create a Milvus custom resource on Kubernetes using KubeDB. Here is the installation process of KubeDB. To install KubeDB on Kubernetes cluster, user can use this helm command and need a license to install it. And user can visit kubedb.com to get the license. Um, In the live demo session, I will use this YAML for Milvus standalone deployment. Here, as the API version, this tells Kubernetes that we are creating a Milvus database custom resource managed by KubeDB. And the API version mainly defines the schema and supported features. In metadata section, we have name and namespace. Here, name is the logical database name used by KubeDB, and namespace determines where all Milvus resources is going to live. All dependent resources will be created under this namespace. In spec section, we have version as 2.6.11 points to the specific Milvus Docker image version from the KubeDB catalog. And for topology mode, we have standalone, which means a single Milvus process. It is best for development, testing, or small workloads and have simpler operational model than distributed mode. Later, we have object storage, which is mainly used for data persistence. Milvus stores all of its vector data and segments in remote object storage, and we use a config secret in this, and this secret mainly contains access key, secret key, and endpoint. And it is typically backed by MinIO or S3 compatible storage. Without object storage, Milvus cannot persist data reliably. Later, we have meta storage. Milvus uses HCD as its metadata store, and it mainly stores collection schemas, segment metadata, and index metadata. Here, we have a field named externally managed. If it is true, that means KubeDB will not create HCD, and an existing HCD cluster is going to be used. And if it is false, that means KubeDB will create the CRD, but an HCD operator should be running in user side. Later, we have disable security. It mainly enables authentication and authorization inside Milvus. Then we have auth secret. It mainly defines how Milvus credentials are going to be managed. Credentials are stored in a Kubernetes secret. And here we have a field externally managed. If it is true, that means KubeDB will not auto-generate credentials, and the user is going to be responsible for creating and rotating them, like we have one named Milvus auth. And if it is false, that means KubeDB will auto-generate credentials on behalf of user. Later, we have storage type, which is durable, meaning we are using persistent storage to keep data safe even if pods restart. And we have access modes as read-write once, which ensures only one pod can write to the volume at a time. And we have resource storage at 10 GB. That means it is going to allocate 10 GB of space. Later, we have our one of the most important field, which is configuration. This section mainly controls Milvus runtime behavior. If the user adds custom configuration via secret, then it will be prioritized over default configuration. And if the user uses inline configuration, then the inline configuration will override both custom configuration and default configuration. Now I am going to deploy this Milvus instance using the Kubernetes custom resource defined in this YAML file. Let us deploy it. Um, if we install Helm, we will have this pod running. By the Helm command, we will have these pods running, and we have applied our MinIO, and thus these pods are running in our KubeDB namespace. So I have applied the standalone Milvus standalone YAML file that I have shown sometimes before. As I have applied this manifest, the operator will take over and start creating the replicas. And here we can see our Milvus standalone pod, which is running. Let us see the PVC according to this pod. This is the PVC which ensures data safety for this pod. And we can see that it is in ready state, which means our DB is ready. Now we will see how we can read and write into Milvus. First, we need to port forward our service. Let us have a look at the service. This is our service, main service, which is located in the port 19530. Let us put forward this service. At first, we have to create a collection. For creating a collection, we need to see what is the username and password. As we have applied a Milvus auth secret for this port, so we need to retrieve it. So here we can see the password is Milvus and username is root. Now I am going to use this password and username for creating all collection and doing all of the retry process. This is the command that is going to be applied for creating a collection into Milvus database. Now, if we describe this collection by this command, we can see our collection is created with this ID, and also an index is created with the name vector and its state is loaded. Now let us load this in order to insert and query into this collection. It is loaded successfully. Now we will insert two vector in our collection. So with ID 1 and 2, this two vector has been inserted into our collection. That means we have completed our write process. Now let us query to get these two vectors. Here it is. We can see with ID1 this and ID2 this that we have inserted previously. So we have been able to successfully do write and read process into our Milvus database. Now we will check how our DB is going to prioritize custom configuration and inline configuration. Let us exec into our port at first. So these are the default configuration that we have applied into our Milvus database. Here we can see that our storage type is remote, and under log the level is info, and for query node there is only port section. If we look at this is the CRD we have applied previously. Now we are going to apply our configuration secret to see how our DB is going to prioritize. Mm. So our secret and CRD has been configured, and we have to delete our port in order to have all the changes. Well, it is getting deleted. Let's have a look what we have changed. Previously it was info, now it is debug, and under query node we have added graceful time which is 10, and in common section we have set a storage type as local. So let's have a look. It will take some time to being deleted the port or being restarted, so that all of its resources should be deleted along with this. If we again exec into our port, so we can see under query node the graceful time is 10, and under log section level is debug, and under storage type it is local as we have expected. Now we will see how our DB reacts with inline configuration. So let us apply this inline configuration. We have to again delete our port to have all the changes. So if we look at this, in inline part, we have set graceful time as 20, which was 10 before, and Under log section, we have set it in info and storage type in remote, which was previously debug and local. Now let us have a look to see the changes. It will a little bit of time to being deleted. Yeah. Now let us exec into it once again. So here we can see the changes as expected. The graceful time is 20, and under log section level is info, and under common section it is remote. Okay. So we have successfully manifest this. Now we will look at our distributed YAML. So here all the fields like kind, name, namespace, version, object storage, meta storage, auth secret, disable security, and configuration all remain similar in the distributed um, part also. So I didn't show them again. Let us deploy this. Before it's being created, let us have a look. So here this the mode is distributed, which mainly enables distributed Milvus. Each Milvus internal service runs as its own workload, and for Milvus we have 5 components: mix coordinator, proxy, streaming node, and other two is data node and query node. Like but by default all components have one replicas, but user can customize it as they want. Like for mix coordinator and proxy we have set 2 replicas, and for streaming node we have set 3. And for proxy, the pod template, in the pod template section we have set its storage also. And for streaming node it has its own PVC, so that's why we have to give the storage part for this streaming node if we are customizing this. Now, if we look at the configuration, we will notice that we did not explicitly specify anything for meta storage or etcd. Previously, it was externally managed through. So in KubeDB, when etcd is disabled or not externally provided, the default behavior is that KubeDB manages etcd internally. Because of this default behavior, KubeDB automatically creates the required etcd ports along with their corresponding persistent volume claims. Um, so if we look at the HCD, all the ports are ready, and if we look at the PVCs, so we can see all of the PVCs corresponding to the ports are bound state. Um, Once HCD is up and running, all pet set will be created and along with their ports. As we have applied one data node by default and one query node, and we have customized 2 mix coordinator, 2 proxy, and 2 streaming node, so all are in running state. Now, these are the mainly 5 core components, each responsible for a specific role in the system. For each of these components, KubeDB creates the appropriate pet sets and pods as we described. And among these components, I want to specifically highlight streaming node. The streaming node is responsible for handling log and streaming data. And because of that, it requires its persistent storage. If we have a look at that, so we can see the PVCs related to this streaming node ports. In addition to ports and storage, KubeDB also set up the required services for each component. Let us have a look. Hmm. The service allow internal communication between the Milvus component and also explore necessary endpoints. And the main service corresponds to the Milvus proxy, which is the main entry point to the Milvus cluster. All client requests such as insert, search, or query go through this proxy. And for the remaining components, the service primarily expose metrics ports. The metric endpoints are extremely useful for monitoring and observability, as they allow tools like Prometheus to scrape metrics and help us track the health, performance, and resource uses of each Milvus Milvus component. So in summary, with minimal configuration, KubeDB automatically provisions etcd with persistent storage and deploys all Milvus components as pet sets and pods, ensures durable storage wherever needed, and they allow tools like Prometheus to scrape metrics, giving us a fully operational and production-ready Milvus cluster. As etcd and pods are ready, and in the behind the scene, and health check is running, and when it is done, our DB is ready. Okay. Now, here are some upcoming features of ours. In some exciting features include built-in monitoring using Prometheus and Grafana, backup and restore, advanced ops requests like scaling and upgrades, and support for newer Milvus versions. So that's all from my side. If you have any questions about this webinar, you can ask me.
So from the audiences, if you have any questions, feel free to ask. Maybe it's about KubeDB or about Milvus, or how KubeDB manages any sort of question. You can ask that. So I guess there is no question at this point. And with that, we conclude our today's webinar. Thank you, Urmi, for delivering an insightful session with a clear and practical hands-on demo. It was a highly engaging discussion on one of the most widely adopted vector DBs, Milvus. As we continue this series, we'll be hosting additional session focused on the other leading vector databases as well. So stay tuned and keep an eye on our upcoming webinar schedule. Be sure to check out appscode.com/webinar to explore our full webinar lineup. Finally, a big thank you to everyone who joined us today and actively contributed to the session. Your participation truly made it worthwhile. Until next time, take care and have a great day. Bye bye. হ্যাঁ, তোমরা চাইলে লিভ নিতে পারো।
ভাই, আমিও কি লিভ নিব?
হ্যাঁ, তুমি লিভ নিতে পারো। আমি ওই যে স্ট্রিমটা শেষ করে তারপরে মিটিং ক্লোজ করবো আরকি।
আচ্ছা।